Alright, so we're going to do another past paper question, this time from the 2006 HSC paper. We're going to focus on question 16, worth 6 marks in total. So it says a projectile leaves the ground at point A, so this point here, with velocity components as shown in the diagram. It follows the path given by the dotted lines, so this tracking here, and lands at point B, so that one there. What we are given is uy and ux. What we can also assume that we know is that the acceleration due to gravity, ay, is 9.8 meters per second squared. So in question 1 it says state the horizontal component of the projectile's velocity when it lands. So we are looking at Vx over here. Now if you recall, when we did our initial assumptions for projectile motions, is there is no air resistance. Okay, so if there's no air resistance, acceleration is effectively 0. And so, if there is no acceleration, there is no change in our velocity. So ux is going to equal to Vx, and we're going to get 45 meters per second in that direction, or let's just call it to the right. Okay, so that's the direction it's going to go. Question B, it says find the magnitude of the initial velocity. So that might sound strange to some of you where we're already given the initial components. What it's actually asking you is the launch component. So the actual component, so the resultant velocity, this bit here, that u there. If we assume this to be, like a triangle, so I'm going to move ux, or ui, sorry, over here and to form a triangle. Imagine it's a right-hand triangle. We can use Pythagoras Theorem to work out the value for u. So u is going to equal to the square root of 40 squared plus 45 squared. And I'm going to put it into my calculator here. And I get a value of 60.2 meters per second. Okay. Now, some of you might ask, how many sig figs should I use? If you actually read the question carefully, it actually rounds off to 2 significant figures. Even the value for A is also rounded off to 2 sig figs. So I'm going to also round it off to 2 sig figs. I'm always going to round off to the smallest number that I used in my equations or calculations. Okay, question C, it says calculate the maximum height, so that's what I'm looking for, attained by the projectile. Now we know that at this point, okay, sy max, so the maximum displacement in the vertical direction, is also where the velocity of the y component is at 0. I'm going to just try and change up my colors so it's not all cluttered the same. So that's what I'm going to look at. Now, the formula that I can use to solve this is, because I already know what Vy is, I know what Uy is. Okay. I also know that added, also know what 2as. Okay, I already know that values. Now some of you might have spotted that I have forgotten to put my squares here, so I'm going to do that now. And that's how I'm going to find the maximum height here. Now there's a couple of ways you can do it. You can rearrange this with the appropriate algebra, or you can do just simply substituting and then rearranging. I'm going to use that method Hopefully they'll make it a little bit easier for everyone to follow. But by all means, if you're comfortable with changing this through algebraic manipulation, go for it. So that's 0 equals to uy, which is 40 squared, plus 2 minus 9.8, and sy there. So when I move everything over, so I'm going to move the 40 over to that side, and then I'm going to divide by that. So I'm going to subtract and then divide. So I get sy is equal to minus 40 squared. So I'm going to do the brackets there, but the end value should be a negative either way. Divided by negative 2 bracket 9.8, which is basically just taking the negative out of what we had just then. So the end value we get, I'll put it into my calculator again, is 80, and we'll just round it off this time, about 82 meters in height. So that's the maximum displacement in the vertical component that we have there. So that's really good. Change colors again because that looks a little bit light to me. And then it says calculate the range. So the range, which is Sx, we do not know that. The other thing is we want to know what, we already know what Ux is. That's given a bit earlier, that was 45. But we do not know what the value for T is. Okay? Let me just check if it is. Yep, so we don't know what T is. Now, a little assumption that we can make, because it's landing at the same height as its starting position, we can do a little estimate or a little assumption. We can assume that the time it takes for it to get up to here, this point, we can call it T, because that is where velocity, the y velocity, is equal to 0. We also know when it lands again, that y velocity is also equal to 0. So I can have two values where Vy is equal to 0, up here and over here, which I'm going to label as 2t. So I'm going to find the time it takes to get to the peak height here. I'm going to times it by 2, and that will tell me the amount of time for it to fall the whole journey. Okay? So the velocity I'm going to use to firstly figure out time is Vy equals to Uy plus AT. So 0 here, 40 here, minus 9.8 t. So t is going to equal to minus 40 over minus 9.8. So the overall value will be about 4.1 seconds. Okay? So next bit, I'm going to try and work out what the displacement is. And the displacement is going to be 45 times 4.1 seconds. And I'll get an estimated approximate value of 148.5 meters in the range. And that's the exact number there, but so there we go. So that's how you do the question for the 2006 paper. Wonderful. Now, keep studying and try this yourself as well.